Imagine a journey not just to another planet or even another star, but to an entirely different galaxy. Billions of light years away, a new cosmic neighborhood awaits. This isn't science fiction, it's a question that fuels the minds of physicists and dreamers alike. Could humanity ever truly travel from our Milky Way to, say, the Andromeda Galaxy? The distances are mind-boggling, the challenge is immense. But what if there were cosmic shortcuts, natural phenomena that could bend space and time to our will? Our first stop on this speculative journey is the black hole. These enigmatic objects are regions of space-time where gravity is so strong that nothing, not even light, can escape. They form from the remnants of massive stars collapsing under their own weight. At their heart lies a singularity, a point of infinite density. The boundary beyond which escape is impossible is called the event horizon. Crossing this threshold means there's no turning back. So, could a black hole be a portal to another galaxy? The idea is certainly captivating. It's a common trope in science fiction, a quick jump across the universe. However, the reality is far more terrifying. If you fell into a stellar mass black hole, the immense tidal forces would stretch you like spaghetti. This process, aptly named spaghettification, would tear you apart long before you reach the singularity. Even supermassive black holes, like the one at the center of our galaxy, pose insurmountable challenges. While their tidal forces are less extreme at the event horizon, the singularity still awaits. There's no known way to survive the journey to or through it. But what if black holes aren't the only game in town? Enter the wormhole, also known as an Einstein-Rosen bridge. This concept emerged from Einstein's theory of general relativity. A wormhole is essentially a theoretical tunnel connecting two distant points in space-time. Imagine folding a piece of paper and poking a hole through it. That hole is the wormhole, connecting two points that are far apart on the unfolded paper. These cosmic shortcuts could potentially link different regions within our own galaxy, or even different galaxies entirely. They offer the tantalizing possibility of near-instantaneous travel across vast cosmic distances. However, there's a catch. The wormholes described by general relativity are incredibly unstable. They would likely collapse faster than anything could traverse them. They'd be fleeting, microscopic tunnels, impossible to enter or exit. To keep a wormhole open and stable for travel, we would need something called exotic matter. This isn't just rare, it's matter with negative energy density. It would exert a repulsive gravitational force, propping the wormhole open. We have no evidence that exotic matter exists in sufficient quantities to create or sustain a traversable wormhole. It remains purely theoretical, a mathematical possibility rather than a confirmed physical reality. Now, let's consider the flip side of a black hole, the white hole. If a black hole is a region from which nothing can escape, a white hole is a region into which nothing can enter. It's like a cosmic geyser, constantly spewing out matter and energy. The concept of white holes also arises from general relativity. Mathematically, they are the time-reverse solution of a black hole. If you could run a black hole's life backward, you might get a white hole. However, unlike black holes, there is no observational evidence for white holes. They remain purely hypothetical. Some theories suggest that the singularity of a black hole might connect to a white hole in another part of the universe, or even another universe. This idea forms the basis of some speculative wormhole theories. Perhaps entering a black hole could lead you out of a white hole somewhere else. It's a fascinating thought, but one without any current scientific backing. So, could black holes, wormholes, and white holes be interconnected? Some theoretical models propose that a black hole's interior might indeed lead to a wormhole, which then exits through a white hole. This would create a cosmic transit system. Imagine falling into a black hole in the Milky Way, surviving the journey through a stable wormhole, and emerging from a white hole in Andromeda. It's the ultimate cosmic express. But again, the challenges are immense. The stability of the wormhole, the existence of exotic matter, and the very nature of white holes are all huge unknowns. We're talking about physics far beyond our current understanding. To grasp these concepts, think of a black hole like a waterfall. Once you go over the edge, there's no climbing back up. The event horizon is that point of no return. A wormhole is like a secret passage through a mountain. Instead of climbing over, you go straight through, saving immense time and distance. But imagine if that passage kept collapsing, or needed a special invisible force field to stay open. A white hole, then, would be like a fountain that never stops gushing water. You can't push water back into the fountain. It only flows out. It's a one-way exit. These analogies help simplify complex ideas, but they also highlight the extraordinary nature of these theoretical phenomena. We're dealing with the very fabric of space-time itself. Even if traversable wormholes existed, the energy required to open and stabilize them would be astronomical. We're talking about energy levels far beyond anything humanity can currently conceive or generate. It would likely require harnessing the energy of entire stars or even galaxies. Then there's the issue of time dilation. According to Einstein's relativity, time passes differently for observers in different gravitational fields or at different speeds. Traveling near a black hole or through a wormhole could mean that while only moments pass for the traveler, centuries could pass on Earth. Imagine returning home to find that everyone you knew, every civilization you remembered, had long since vanished. The journey itself could be a one-way ticket to a vastly different future. So, is intergalactic travel through black holes, wormholes, or white holes possible? Based on our current understanding of physics, the answer is a resounding not yet, and perhaps not ever, in the way we imagine. Black holes are destructive, wormholes are unstable and require exotic matter, and white holes are purely hypothetical. The laws of physics as we know them present formidable barriers. The energy requirements are staggering, the stability issues are profound, and the very existence of the necessary components is unproven. However, science is constantly evolving. What seems impossible today might be understood differently tomorrow. Our knowledge of the universe is still in its infancy. While direct travel through these cosmic phenomena remains firmly in the realm of speculation, the pursuit of these ideas pushes the boundaries of our understanding. It forces us to think about the fundamental nature of space, time, and gravity. Perhaps future generations will discover new physics, new forms of matter, or entirely new ways to manipulate space-time. Until then, the dream of intergalactic travel through cosmic shortcuts remains a powerful inspiration. It reminds us that the universe is full of mysteries, waiting to be unraveled by curious minds.